This video is about how Devonian geology controls lithium brine resources in Alberta and Saskatchewan. We're going to look at the advantage of exploring for lithium in the Duperow Formation in Saskatchewan versus the Leduc Formation in Alberta. And this slide just shows one simple example comparing E3's reported results of 75 milligrams per liter concentration in central Alberta to that of Arizona Lithium and EMP Metals in southern Saskatchewan at 111 and 200 milligrams per liter respectively, and also noting that maximum concentrations in Saskatchewan do go up to 259 milligrams per liter. We're going to look at why EMP has what is probably the highest quality lithium brine resource in Canada. Lithium concentrations in Saskatchewan are much higher than in Alberta. That brine in Saskatchewan is free of oil-filled impurities, and therefore it's straightforward to produce and process. There are multiple reservoir zones in Saskatchewan. They are predictable and laterally continuous over all of southern Saskatchewan. And finally, EMP's land base is characterized by relatively shallow drilling depths of about 1,800 meters down to the top of the Duperow Formation. We'll look at all of these points in detail, but to understand how some of these attributes came about, we need to delve into the Devonian geology a little bit. And to do that, we'll start with a cross-section. Now, a cross-section is just a slice through the earth, and in this case, that cross-section goes from northwest to southeast, starting in northeast British Columbia, traversing across central Alberta and right down into southeast Saskatchewan. So you're looking at it side on from the south so that northwest is to your left and southeast is to your right. The two formations that host lithium brines in the Devonian are the Leduc Formation in Alberta and the Duperow Formation in Saskatchewan. You can see from the cross-section that they are of the same age. They're at the same stratigraphic level. However, they are shown quite differently, with both a name change and quite a major break here, roughly around the Alberta-Saskatchewan border. And that's because the way that these sediments were deposited is really quite different. The Leduc Formation in Alberta was deposited as a series of reefs built out into the open ocean. They tend to be vertically stacked, quite thick, but laterally not very extensive. The Duperow Formation, in contrast, was deposited on a very broad, shallow carbonate platform. It was a hot and arid environment, so there were many cycles of deposition and evaporation. This led to cyclical deposition and a type of layer cake geology where there are many stacked reservoirs, none of which are very thick, but all of which are laterally very extensive. They go for tens or even hundreds of kilometers. To understand this better, it's nice to look at it from the top down. So the previous slide was our side-on version. Now we're looking at a map from the top down. This is a paleogeography map, and paleo just means in the past. In this case, it's at the Devonian times. So it's just a simple depiction of what the geography or the landscape might have looked like at the time those sediments were deposited about 375 million years ago. In central Alberta, you can see these light blue features, which are the Leduc reefs deposited out into the open ocean or this shale basin in central Alberta, and contrast that with this platform interior or shallow water platform carbonate of the Duperow Formation in Saskatchewan. In order to understand what the deposition was like during that time period, it's very helpful to look at modern day analogs. And a good analog for the Leduc Formation in Alberta, not a perfect one, but a good one might be the Great Barrier Reef of offshore Australia. You can see some of those features that we mentioned. There's the open ocean in the background, and then there's a long linear feature deposited out into it. The Duperow Formation was probably a bit more like the modern day Bahamas platform. And in this photo, you can see there's the open ocean in the background with some connection, probably a lot more restricted than it was for the Leduc. And you can see in the foreground several different environments. There's probably a channel in this area of the photo. There's some emergent land masses. There's some shoaling features, and probably even some sandbars in the foreground of this photo. All of those environments were quite likely present when the Duperow was deposited. So what we'll do now is we'll blow this up and look at some real world data. So we've blown up Saskatchewan, Alberta here, and we've taken off everything except for the important elements, which are the edge of this Duperow shallow water carbonate and some of these Leduc reef trends that are built out into central Alberta. And on top of that, what we're showing in blue dots are all the wells that have been tested for lithium in those two provinces. There are about 1,500 wells in Alberta and probably about 100 wells in Saskatchewan. We can look at companies that are exploring in the area, and all the areas of interest are shown by these red dots. If you're familiar at all with this space, you'll probably be quite familiar with some of those names. We've already mentioned E3 in central Alberta, the Clearwater area, as an example. And of course, of particular interest is Arizona Lithium and EMP Metals in southeast Saskatchewan. Where things get really interesting is when we start posting the lithium concentrations that were tested by those companies in those two provinces. There's a very clear trend that emerges if you look closely at this data. There's kind of a background lithium concentration in Alberta of about 75 milligrams per liter. Sometimes lower and sometimes a little bit higher, but that 75 milligrams per liter, it seems to be like a background average, and it's what EF3 is reporting for their Clearwater project. If you look at southern Saskatchewan, the numbers are much higher. Both Arizona Lithium and EMP Metals have tested much higher numbers at 111 and 200 milligrams per liter, respectively. Now, there are several ways to compare lithium concentrations, but what we've chosen to do on this slide is use empirical data. So both EMP and Arizona did an extended well test with all of their Duperow zones open to perfs at the same time. So comparing these two tests kind of gives us a blended lithium rate that makes it quite reasonable to compare apples to apples among those two companies. And that's how we got to these two numbers that you see here. And we do note that there is a range. Some of the numbers are a little bit lower. Occasionally we see down to 50 milligrams per liter, but we have also recorded up to 259 milligrams per liter to date. Final points to make on the Duperow formation in Saskatchewan are quite important. Why are those concentrations so much higher than they are in Alberta? Well, the theory goes that these evapo-concentrated Devonian seawaters are what produce high lithium concentrations in the present-day Duperow aquifer brines. We know that evaporation concentrates minerals, and in our case in southern Saskatchewan, that makes these brines enriched with regards to lithium. The second point is extremely important. Those lithium brines in Saskatchewan are clean. They're free from oil-filled contaminants. In contrast to all of the operators in Alberta, who have to deal with hydrogen sulfide and residual oil, none of those components are present in the brines in Saskatchewan. They're clean and they're therefore easy to process into the final product of lithium carbonate or lithium hydroxide. So what we'll do now is zoom into southeast Saskatchewan and look in a little bit more detail at EMP's project in southeast Saskatchewan and how it compares to Arizona Lithium. So this is a blow-up of that southeast corner of Saskatchewan. And for scale purposes, these blocks are townships. One township is about 6 miles by 6 miles, or roughly 10 kilometers by 10 kilometers. EMP lands are shown in the blue polygons, and names of some of those land blocks are highlighted in blue as well. On top of that map, what we've posted is a lithium bubble map. And this is kind of a standard way of displaying varied concentrations over a big area. So the bigger the bubble, the bigger the lithium concentration that was tested at that well. And in cases where you see several bubbles on one well, that means that there were several zones tested in the same well. What we see here is the 3 wells to the south are owned by Arizona Lithium, and they had good results, over 100 milligrams per liter and occasionally over 150. But the best results are to the north over EMP lands, where EMP has tested 3 wells well over 200 milligrams per liter. And you can see a lot of these bubbles are quite big in size, indicating quite a big resource that is extensive over quite a large area. Keep in mind, the north-south distance here is over 30 kilometers. And the east-west distance is over 70 kilometers. So you're looking at well over 2,000 square kilometers of area. It's a big resource. Comparing to Arizona, it's useful to look at a structure map on top of the Duperow Formation. And a contour map, a structure contour map is just like any other contour map. It shows a surface. The only difference is that this surface is quite deeply buried. These contour intervals are 50 meters apart, and they get deeper as you go down to the south, as you can see from the inset legend here. So Arizona's lands are quite a bit deeper than EMP. And if you want to look at some averages here, well, if you kind of take an average contour through Viewfield South, Midale, and Mansard, you're looking about 1,800 meters to drill down to the top of the Duperow Formation, give or take. If you look at Arizona Lithium and you want to get an average, well, it varies from, say, 2,200 to 2,500 meters to get down to the top of the Duperow Formation in that area. So why is this important? Well, for a couple of reasons. Obviously, if the deeper you have to drill, the more expensive it's going to be. So therefore, you're going to have higher capital and operating costs. Secondly, all things being equal with regards to reservoir, if you take a rock and bury it a few hundred meters deeper, that rock is going to experience some compaction and therefore some destruction of porosity and permeability. So what you might get from this slide is that EMP is in kind of a sweet spot with high lithium concentrations and relatively shallow drilling depths, and there are also good reservoirs throughout. Now, we've mentioned reservoirs and reservoir quality here, and so we're going to finish off the presentation here with looking at those in a little bit more detail. We'll do a cross-section on the next slide that collects up data from Mansard to Mansard South through to Midale, Viewfield South, and then Viewfield North, so we can look at what the reservoir distribution looks like in an east-west sense across EMP's lands. So those are the areas that we're looking at. The top of the Duperow is shown in blue, and you can see several horizons of interest that are color-coded. There are 11 zones across our lands that have potential for lithium development in the area. There's 2 in the Hatfield, 2 in the Saskatoon. There are 6 Y-mark members of interest, and 1 in the Seaward Evaporate. On this cross-section, the only zone that is not prospective for lithium is the Flat Lake Evaporate, which is highlighted in green. And if you recall, we talked about cyclical deposition and then periods of evaporation. Well, here's a classic example. The Flat Lake Evaporate was one of these evaporative events, and it is therefore not prospective for lithium, but all the other ones are. And they've all been tested extensively, as you see on the next slide here. All of these blue circles are zones, or where these zones have been tested and measured geochemically for lithium concentration and other minerals. So what the takeaway from this slide is that EMP has an extensive database over a very large area. So we have a very good idea of the lithium concentrations per zone and how they relate both laterally and vertically throughout the section. And when it comes to reservoir quality, we also have very good control on that using petrophysics and mapping to determine which of these zones are better than others. I did mention that reservoir is present everywhere, but it does vary in quality, of course. But using the mapping and petrophysics, we can high grade the zones that are the best reservoir quality and use them first in our development schemes. And those zones, it turns out, are in the upper part of the Y mark. So if you look closely at our PEA that was published, you'll see that that contemplates developing the upper part of the Y mark first because it has the best reservoir quality and the best lithium concentration. To finish off the presentation, we'll look at some conclusions here about EMP's lands in southeast Saskatchewan. So far, the highest known lithium concentrations in Canada come from this area. That lithium brine is clean and free of oil field impurities like hydrogen sulfide and residual oil. Therefore, it's straightforward to produce and process right to the final sellable product, which would be either lithium carbonate or lithium hydroxide. There are multiple reservoirs in southern Saskatchewan. They're predictable and laterally continuous all across the southern part of the province. And finally, EMP's lands are characterized by relatively shallow drilling depths of about 1,800 meters. That concludes today's video. I hope it's provided some perspective on how the Devonian geology is controlling this very high quality lithium brine resource in southern Saskatchewan. Thank you.